finish our story about the hydrogen atom. Okay? So just to summarize what we did yesterday, we started from the Hamiltonian for the relative motion. So P squared over twice the reduced mass minus Z P squared over the distance from the origin. We wanted to solve this, okay, in particular for the bound states of this problem. We realized that P squared contains in fact L squared, okay? Therefore we separated the wave functions into a radial part times spherical harmonics. Okay, we realized that R should depend on L, and in principle there is another index K which classifies the solutions of the radial problem. Okay, so there was a radial problem that comes out of this. We realized that in fact there is a much more useful radial function, which is U being R times R. Okay, so you multiply by R. This is essentially the nice one-dimensional radial wave function that you can think of solving. And in terms of that, the radial equation, let me remind to you what was minus 1/2. The second derivative of which we decide to indicate in this way. This is the dimensionless wave functions, which I omit the tilde. Okay, and then we had something like this over twice rho square. Rho is the dimensionless distance from the origin in terms of the Bohr radius. Minus 1 over rho, this is the Coulomb part, times UKL is equal to E tilde KL times UKL, where this is again the energy divided by the Hartree energy. Okay, so we saw all this in detail. And then we realized that the form of U should be respecting some precise limits when the distance goes to infinity and when the distance goes to 0. And we made an ansatz, which is essentially that U KL of rho was equal to some W times an exponential. Okay? This object, we know it should start like rho to the power L plus 1. And so we wrote it as sum over Q from 0 to infinity of CQ rho to the L plus 1 plus Q. Okay, so that the first term is proportional to rho to the L plus 1, and the other ones are increasing. And then we realized that we should really not have an infinite power series, otherwise there is no bound state discretization condition. And in fact, we found a recursive relation for this coefficient. I remind you that the recursive relation was, let me copy. I write it here. CQ equal to twice lambda KL times Q plus L minus 1 over Q plus 2L plus 1 times CQ minus 1. Okay, this was the recursive condition that we derived, and we said the power law must terminate to some precise integer k obviously greater or equal to 1, at least the zero order term should be there. Okay, so this is the condition. And from this condition you immediately deduce that indeed lambda KL should be equal to 1 over K plus L. So K is the radial quantum number, L is the angular momentum, and this combination of two integers defines the principal quantum number N. And we also know that lambda is related to the energy in the following way. E tilde is of KL is equal to minus 1/2 the square of this lambda. Okay? So with this we deduce that indeed the bound states of this problem should be given by this object. Okay? So this is what we, essentially what we did yesterday. Okay? Is it? Good. Now let's see a little bit closer the structure of these solutions. So the first thing that I notice is that the ground state is obtained for, okay, so if this is say 0, okay, above here, as I told you, there is a continuum of states that we are not looking at. So I'll write here the E tilde and the first, so E over the R, if you want, okay. The first state is here at minus 1/2, okay. 1/2 Hartree is in fact the Rydberg, so 13.6 electron volts. Okay. Now this state is associated to n equal 1. You see? But n equal 1 can be realized. Remember that n is equal to k plus L. K should be greater or equal to 1. L should be greater or equal to 0. Okay? There is only one way in which you can make 1 out of two integers with this constraint, which is having k equal to 1 and L equal to 0. Okay? Good. So L equal to 0 immediately implies that you have only one spherical harmonics, which is the 0, 0, right? This is the reason why this state is called the 1s state. S reminds us of this L equals 0 thing. What about k equal 1? K equal 1 is telling us that the radial function, or better, the polynomial part of the radial function always has this decreasing exponential related to the energy, by the way. Okay? So this is a piece. But the radial function contains only C0, and C1 is already 0, you see, for k equal 1. Okay? So the radial function of this object here would be C0 times rho to the Q is 0, L is 0 times rho, okay? Times e to the minus lambda 1, 0 rho. This is the U, okay? But remember that U is actually R or rho times the radial function. So if I ask you what is the radial function associated to this object, so to this, say, 1, 0, okay, state, you would say that this is C0, the coefficient, times e to the minus lambda 1, 0 rho, okay? So the radial function of this orbital is simple decreasing exponential without nodes. This is the typical shape of the 1s state. You can find the normalization coefficient. This is fixed, okay? This is absolutely fixed, and it is equal to 1. You see, for n equal 1 is 1. So the object is C0 e to the minus rho. Now, notice rho is R divided by the Bohr radius. Okay, so you know precisely the decay in whatever units you want. Is it clear? Good. Only one state here. Let's move on and let's look at n equal 2. Now, you can make n equal 2 now, either with n equals 0 and k equal 2, right? So, first of all, n equal 2 has an energy which is minus 1/2 times 4, so minus 1/8. Okay, I draw it here, although it's probably not nicely in scale. Never mind. Okay, so one possibility is for this n equal 2 is k equal 2 and L equals 0. Okay, you would call this state the 2s state. The second possibility is, however, k equal 1 and L equal 1. Okay, so there is another possibility which is k equal 1, L equal 1. Now, L equal 1 is a state associated to a spherical harmonics 1, and you know that it comes with an index m that assumes 3 values. Okay, so this is not a single state, but actually 3 states. Okay, there are a total of 4 states, if you include both, totally degenerate because they all have n equal 2, independently of what is the mixture of k and L that they do. Okay, so the excited state of the first excited state of the hydrogen atom comes from 2s states and so-called 2p states, but they are totally degenerate. Let's try to extract the radial functions of these things. Okay? We have to play a similar exercise. Let's first do the 2s. Okay, I do it here. So I know that the 2s has k equal 2, which means that I have C0 and C1. C1 is, however, perfectly fixed. You put here Q equal 1, okay? So it is equal to twice. Then I have this lambda. Lambda in this case is, by the way, since n is equal to 2, is 1/2, okay? So 2 times 1/2 is the lambda, and then I have Q, but Q is 1 plus L, L is 0, so 1, 0, minus 1 divided by, I put here Q equal 1, 1, 0 and 1. So this is 2 times 1. So if I have done no mistake, here I have 2, and this is C0. Okay? So C0, you use it as a normalization. C1 is absolutely fixed. And is equal to, let's see, this is 1/2 minus 1, so it's minus 1/2, by the way, this goes. So it's equal to minus 1/2 C0. Is it correct? I think so. Okay? So let's write the U for the state 2, 0. That would be C0 times, so L is 0, so rho to the 1 plus 0, rho, plus C1 times rho, square, okay, times e to the minus the lambda, which, if you remember, is 1/2. Okay? So let me rewrite it as rho times C0, but remember that this is minus 1/2. So in fact, I write it like this: 1 minus 1/2 rho times e to the minus rho over 2. Okay? And once again, if I want the R, all I have to look at is this. Okay? So let's plot a little bit things. So the 1s state was something like this. Okay? In terms of R. And in terms of R divided by the ball radius. This other object, first of all, has here R over 2 RB, which means that the overall decrease is slower. But also it has a 0, right? So if I have to plot it, okay, apart from the normalization coefficient, which I should adjust, so let me start from any place, it would do something like this, and then something like this, okay? So there is a 0 in here, right? Precisely at position 2. Okay? Is it clear? Okay, so the 2s state has a 0 at the finite point, and then it decreases slower. Let's see the 2p, just to make a list at least of this. So the 2p now has k equal 1. Okay, k equal 1 means that you have only the coefficient c0, because c1 is 0. Okay, so the c0 only is there, and therefore the u for k equal 1 and L equal 1 would be, let's see, c0 times rho, L is 1, so 1 plus 1, 1 plus 1 is 2, okay? Q is 0, and then I have e to the minus the lambda, still 1/2, so rho over 2. So same slope, but here I have rho square. So in terms of R, I would say that this is rho C0 rho e to the minus rho over 2. Okay? In other words, if I have to draw the 1p state, it would start from 0 here, do something linear, and then decrease again slower than this, pretty much as this would decrease. It's not a perfect drawing, okay? If you do it with a computer, you will nicely see both things. But the interesting thing is that the p state has a node in the origin, while this has a node there. Okay, so this is the 2p wave function. And in principle, you can normalize. Okay? And in exactly the same way, you can construct here the 3 n equal 3 states, which are at, so for n equal 3, you have 9, 18. Okay, so minus 1 over 18. And you will have the 3s, which is again k equal to 3, L equal to 0. Okay? One state. Then you have the 3p, which is k equal to 2, L equal to 1. And then you have states with k equal to 1 and L equal to 2. L equal to 2 means 5 states. 1, 2, 3, 4, 5 states. Okay, the 3D. You can similarly construct the radial wave functions. Okay, is it clear? Okay? These are the atomic wave functions of this object. Okay. I think that this illustrates roughly how to fully solve. And notice this very strong degeneracy that you have of all states. The degeneracy is broken as soon as the potential is not exactly 1 over r. Okay? If you calculate similar eigenstates, for instance, numerically, for a central potential where there are even slight corrections to 1 over r, you would see that this exact degeneracy would be split. In particular, well, obviously the degeneracy between the different m states is not broken because the system has central potential are always invariant by rotation. We'll discuss about symmetries later on, but quite clearly only L enters, not M, and therefore the different M states would be perfectly degenerate, but in general these objects can be different. And similarly here. And in fact, when you consider real atoms with more electrons, even if you try to look for some kind of mean field picture, so each electron has living in the average field due to the other electrons occupying their own orbitals, you realize that the potential is not exactly 1 over r, even in mean field, and therefore at the mean field level you already have this effect. Okay, so this degeneracy is a sharp fact of the hydrogen 1 over r potential in the non-relativistic approximation. You might say, what happens if there are relativistic corrections? This is, we'll see later. There are still some degeneracies, which can be accounted for by just doing some perturbative calculations. Indeed, there are eventually experimentally small shifts, which are called lamp shifts, which I will discuss later on. Not because we will calculate them, but because you have to be aware that experimentally you can do very precise measurements of the spectrum of hydrogen, and this level scheme that I described is not precisely found in the experiment. There are small splittings of levels that I will discuss later on. Okay, clear so far? Oh. Good. So let us move to some discussion of, I think I can erase most of the things here. Some discussion of non-relativistic effects. The reason we discuss those is because they introduce effects which couple the spin of the electron to the orbit. So we discussed already the spin in isolation. We anticipated that spin and orbital are not necessarily disentangled. They could play games together. But I want to describe this now in more detail. Okay? So, if I tell you so far, suppose that I put the hydrogen atom in a classical magnetic field, and I ask you, okay, let's write the Hamiltonian. Then you would say, you would write the following Hamiltonian. Not this, but rather this. P plus E over C, a vector potential. Notice this is a classical vector field. which is the vector potential, which describes the magnetic field that I'm imposing on my system. Purely classical. I'm not treating the magnetic and electric fields or whatever in any quantum way as photons. Okay, this is just a standard classical magnetic field. So that is the kinetic energy, which we would write in classical mechanics. And I remind you that this term is what gives rise to the Lorentz force, okay? The force that bends classical charged particles, like the electron is. Okay, obviously then there is the term, okay, let's write it for a single, for z equal 1, that's enough, okay? And then we say, but no, if there is a magnetic field, then I have G0, mu b, and then I have the magnetic field dotted into the spin operator. The spin operator has no h bar, by the way. The h bar is gone here. This is E h bar over 2 times the Bohr magnet. Okay? So this would be the Hamiltonian that you would write for me. Okay. Now, as you see, if I turn on I turn off the magnetic field, this disappears, and this disappears, and you return to that. On the contrary, I will now argue that the spin appears even in absence of magnetic field in the Hamiltonian through a small term, which is called the spin-orbit coupling. Okay? Incidentally, this is called the Zeeman coupling. Okay? And this thing is called the orbital modification of due to the magnetic field. So the magnetic field modifies the orbital part as well, and it couples to the spin. These are the two basic. Yeah.
So can the orbital momentum couple with magnetic field L?
Yeah. Yes, it is.
Oh.
It is already there, hiding.
Ah, yeah, in the P. Okay. Yeah.
It is here.
Yeah.
Okay. I will discuss probably later. Okay. Suppose that I have a uniform magnetic field. Okay. And you write A in a scalar, in a gauge, where you write this as B dot R or dot S, okay, over 2. This is called the symmetric gauge. Sorry for this is the vector, but let's write it like this, okay? Is the vector product. You can verify. It might have a wrong sign, but either this or the other, that if you take the curl of this A, you get B. Okay? So this is a way of representing the vector potential associated to a uniform field. If you put it there and you do your square things, you will notice that there is a term x vector p that comes out. Okay? You can prove it. So in some sense here there is a coupling between L and the magnetic field, which is in fact very similar to that. You can prove that is of this form. Okay? Plus obviously a term that is b squared, that is the so-called diamagnetic term. So yes, the orbital degree of freedom couples to the magnetic field in here, and as a matter of fact, in a way that is totally similar to that. This is a simple thing, but let me, for the time being, drop it. We can do it. We can do it later. Okay. So let's concentrate again on this magnetic field term. You might say, okay, there are effects due to the orbital and there are effects due to the spin. Yes, if you consider the fact that there is a spin in your problem, first of all, you should double all these levels, okay? So suppose that there was no magnetic field whatsoever. The levels that I drew here are in fact two of them. I draw, they are totally degenerate, obviously, but one is associated to the spin up, and one is associated to the spin down, right? In the same way here, and here. Okay? So in fact, there is an extra degeneracy associated to the fact that you can put the electron either with the spin up or with the spin down, same energy in absence of magnetic field. In presence of magnetic field, this level split. For instance, this thing would split into two levels, okay, due to the fact that the B favors, for instance, the down. The down spin, okay, goes here, and the up spin goes here, with a splitting which is proportional to the magnetic field. Now, you should have a feeling for this splitting. They are very, very small, okay? In some sense, this has already a relativistic effect. You see the C there? If you try to estimate how big is this value for a magnetic field, which is not small like Tesla or so, which are reasonable magnetic field. In the lab, they can do up to 10, 20 Tesla, but these are generous magnetic field. And yet, this effect would be of the order of 10 to the minus 5 electron volts, okay? So think of this being on the scale of 10 electron volts, and this is just a very minute thing. So the magnetic field would split weakly the spin levels. Okay, but that's not the whole story. It would seem that this is the only effect of the spin, and that in absence of magnetic field, there is just a duplication of up and down perfect degeneracy. No, that's not the story. Okay, let's see a bit more about relativistic effects. So the first source of relativistic effects, in fact, is in the kinetic energy itself. Okay? So I must just warn you that when you write this object, you are actually approximating your theory. Remember that in relativity, classical relativity, the relativistic dispersion is in fact the square root of p square c square plus m square c to the 4th. Okay? You remember that this is the correct relativistic dispersion. For a particle of zero mass, obviously this is just p times c. This is typical of the photon. But for a particle with a mass, like the electrons or any other thing, if you expand this thing close to p equals 0, the first term that you get is in fact mc squared. That's the famous mc squared, obviously. So it's the rest energy for a system which has no momentum. Okay? The mass gives energy. And if you can play with this energy to break and annihilate and regenerate particles, that's obviously an important source of energy, which however is not in our department in some sense, because we do low energy physics. Condensed matter is low energy physics. It's your colleagues in high energy which can somehow make particle collide, annihilate and generate new particles. And at that point, whatever masses you have in the game, they will enter into the energy balance. For us, an electron is there and you don't touch it. So in some sense, this object is always there for us. But then the next term in the expansion, you see I can write this as square root of 1 plus, let's see, p squared c squared divided by m squared c to the 4th. Okay, that is exactly the same expression there. So if I expand this, I find mc squared times 1 plus 1/2 of this, okay, plus or minus, I think it's minus, and I think it's 1/8, if I remember well, the square of this. So p squared c squared over m squared c to the 4. Okay, so I am expanding the square root. Look what happens. The first term is the famous mc squared. The second term is plus 1/2. Let's see. You have a p squared. This is already m squared times c squared, but you have to multiply by an m, and therefore this becomes m, and the c squared eliminates this. There it is, p squared over 2m, okay? So out of this object here, which if you plot, it's something like this. So it starts from mc squared, and then it has this funny shape. Here comes the first term, which is the quadratic dispersion we are always thinking of, okay? Which is this. Obviously, if you insist a lot, the quadratic dispersion is not particularly good. For very large momenta, okay, you can disregard this term, and this goes approximately linear. But this happens for very, very small, very, very large momenta, where obviously relativistic corrections are important. But typically, in our game, it would be enough to be happy about the first correction to that. And the first correction, it's simple algebra. You can write it as minus 1/2 over mc squared times p squared over 2m squared. Okay? You can rewrite it in this way. So you see, this is a square of energy divided by the rest energy of the electron. So it's an energy. The dimensions are correct. Okay. It is interesting to try to estimate the order of magnitude of this effect. And you see, this must be of the order of the kinetic energy of the, say, hydrogen. Now, the kinetic energy of the hydrogen is of the order of the Rydberg. Obviously, there is a compensation of Coulomb and kinetic energy, but essentially it is of the order of the Rydberg. Okay? So if you try to estimate how much this is smaller than this, you see here you have p squared over 2m, and here you have something that has a further factor, p squared over 2m divided by mc squared, right? So p squared over 2m divided by mc squared is how much this is smaller than this. Order. Now, this you can estimate as being the Hartree divided by mc squared. Is it clear? Okay? It's dimensionless, right? Energy over energy. Now, Hartree is of the order of 27 electron volt. The rest mass of the electron is mega electron volts. It's a huge energy, which we never care about, but it's huge. Okay? And in fact, you can just give an estimate. Remember, R3 is m e to the fourth divided by h bar squared. This is mc squared. So the mass goes away, and this ratio is in fact e squared over h bar c squared. Okay? Now, obviously, this is a dimensionless ratio, so this object here is dimensionless and is made of charge of electron, h bar, and c. This quantity here is very important. It's called alpha, is called the fine structure constant. The name fine structure will be clear in a while because it determines little splittings in this scheme of states that I drew at the blackboard. Okay? So you will see. But numerically, this is a famous number, 1 over 137, approximately. It's not perfectly. There are lots of numerologists, okay, around, which they keep writing to you emails that they have discovered theories of everything, okay, in which they explain with numerological arguments why the fine structure constant is 1 over 37. So this is an experimental number, which is approximately of that size, but is not 1 over an integer, okay, by no means. Nevertheless, as you see, if you square this number, this is of order 10 to the minus 2, this is of order 10 to the minus 4. Okay? So this correction here is relatively smaller than what we usually account for, at least at the sizes of P that are important in the hydrogen atom. Okay? Obviously, as you move in the periodic table, there could be atoms where some of the electrons, especially the deep ones, move at much faster P's in some sense, and at that point you should be worried about relativistic effect. What do you do in that case? Well, you don't quite proceed in this way. You try to treat the theory in the correct setting, which is not this, but the Dirac theory, okay? Which is a slightly more complicated issue. And the complication is essentially the following. If you try to just directly use this formula, you see that here there is P squared. If I think of P squared as the Laplacian, this is the square root of the Laplacian. Now, the square root of the Laplacian is not plus m, it's not a nice object, a nice operator, okay? You realize that in some sense it is an operator that if you expand, it has derivative of all orders, you see from here, okay? So this way of proceeding would not be nice. It would give you a very non-local aspect of the story. So it was thanks to the genius of Dirac that he understood how to cope with this square root, okay? And he did it by enlarging the set of components of the wave functions, which is not just a wave function, but is a spinor wave function. In fact, a 4-component object, okay? So he understood this, he wrote his equation from which, in the appropriate limit, this emerges and also the spin emerges automatically. And the spin orbit coupling that I will discuss in 5 minutes also emerges. So the right way to proceed is to start from the Dirac equation and take the non-relativistic limit and start throwing away, if possible, things, okay? And by the way, there are people in condensed matter who work with heavy atoms. They do electronic structure calculation. They do account for relativistic effects by, for instance, starting from the Dirac equation and not from the Schrödinger equation. So it's not fantasy, it's things that if you want to treat, I don't know, some heavy atoms, uranium or whatever, you have to account for those things. Okay, let's cut this discussion here, just to let you understand that the typical size of the correction is this. Okay, now spin orbit. So I erase this kinetic corrections, and I try to argue with you that there are other corrections which have precisely the same sides. Okay. Think of here is the nucleus. Okay. Glass. It exerts, obviously, let's think classically, an electric field. Okay, the electric field is going radially out. So if this is, say, plus E, here I have an electric field at a certain distance r equal to x. I have an electric field that, as you know, is E in magnitude E over the distance squared. Okay? Now, it is radial, so I can also write this as x divided by r. Okay? This is the right direction. X is this vector. Okay. Good. Now, this is the position of the electron. The electron is somehow orbiting on this object. Now, suppose that you are staying on the electron. in the rest frame of the electron, what you see is if you have some momentum or some velocity, okay, here, here, some velocity or some, what you see is that the nucleus is in fact an opposite velocity. You see the nucleus moving, but you know this is a charge, and this charge is moving. So what do you expect? You expect that this will, in fact, give a small magnetic field to you, right? So by sitting on the electron, you actually see the magnetic field generated by the nucleus that is moving in the opposite direction as you move. And, well, you can show that somehow the effective magnetic field that you see is related to the velocity that you have, and in the following way. Okay? So if there is an electric field, then there is also a magnetic field depending on the velocity in this typical way. So V over C vector potential E. Okay? So in this configuration, there would be a magnetic field somehow going out of the blackboard. All right. Now, but if there is a magnetic field that the electron sees, even in absence of a true magnetic field, because after all, I'm not accounting for an explicit magnetic field, but just a field induced by the fact that somehow it's a relativistic change of frame. So if I sit on this thing, an electric field is seen also as an effective magnetic field. And magnetic fields typically act on the spin. So you expect from this that there is in fact a term that is mu B, B effective, dotted S, the spin. Okay? This is the only thing I want you to accept. So even if the actual B was 0, so there is no explicit Zeeman term, the very fact that the electron is moving generates, as seen by the electron, an effective magnetic field proportional to the velocity and to the electric field at that point. Okay?
This B effective is obtained by some kind of changing of the frame of reference.
Right. In principle, this is the correct thing of doing this.
This is doing this. We have to make some Lorentz transformation for
Absolutely.
But since the atom from the frame of reference of electron is moving in a circle, it's not inertial.
Correct. No, I mean, don't think of this as a derivation, okay? So the correct derivation is again starting from Dirac and doing the appropriate non-relativistic limit. Nevertheless, you can try to argue in this kind of way, thinking, sure, obviously. I mean, even the idea of following the electron with a certain velocity is intrinsically non-quantum. So there are several pitfalls in this kind of derivation, but it gives the correct answer. That's the only beauty of it, okay? It's an amazing thing. If you start from the Dirac equation, and if you do the correct non-relativistic limit, you get this, okay? And you get also something which comes out of this, okay? So you're perfectly right. There are no two inertial frames, and you cannot easily make this argument rigorous. And it is not. In fact, you might argue, why don't you put the G0, the factor 2? If you put the 2, it's wrong. Okay? So the correct result comes here, while here you have a factor which is roughly 2, which cancels this. By the way, here there's no 2. Just accept it. It's not a rigorous derivation. It's an argument, okay? To say that could be a term like that. Let's analyze it better. I'll do that here. So you say, okay, let's see, mu B, B effective, dotted the spin operator. Now that is, let's see, mu B divided by B effective is essentially let's change sign. So I write it as E vector V, okay, dotted into S. Now, E. E is in fact this object, okay? So let me write it as mu B over C, and then I have E, the electric charge, divided by R cubed, and then I have X. Well, again, there is an ambiguity in my symbols, so let me use this wedge to denote the object, dotted into S. And now let me just divide and multiply by a mass, okay, in such a way that this becomes the momentum. And this is essentially, let's see, yes, okay. So the result can be put in this form. It is essentially the angular momentum, you see, that is there. So it is equal to mu B E divided by MC R cubed. And then I have the angular momentum dotted into S. Okay? So this is what this term suggests. And believe it or not, it is exact. I mean, it is the correct thing that you get from the Dirac equation. That's the only firm justification.
Why does it work? Like,
I don't know.
this argument is absolutely wrong,
It's,
but it gives correct result.
It is mathematically wrong, but physically meaningful. I understand. Okay? But I mean, the basic of it is that the electron sees an effective magnetic field because somehow there is the nucleus is a charge that is moving. Okay?
In that sense,
every single other detail is highly questionable. Okay? But in some sense, there is some physics behind it. It is okay. So it is nice that with this simple formula, you get, in fact, something which is what you can derive from the Dirac equation. That's the only firm justification of it. I totally share your thing. But okay, this is what happens. Now, you see this object here is called the spin-orbit coupling. It's in fact not a constant. It's a function of R so far. So somehow this piece of Hamiltonian depends on the spin degrees of freedom, on the orbital angular momentum degrees of freedom, which you remember are theta and phi and derivatives, and on the radial part as well. So it's not a single constant. It depends on the distance from the origin as well. The interesting thing is that this you can estimate, and is again a small quantity. Remember, these are dimensionless. I'm here putting in fact, okay, no, let me just, yes, I should put the, another h bar here, okay? So that this is L without h bar, okay? So this is L without h bar, this is S without h bar because the h bar was there, and that's the spin orbit coupling. Now let's see what it is. It is equal to, let's see, E h bar divided by 2mc. Oh, this was the Bohr magneton. Okay, so I'm writing in the Bohr magneton. Then I have E h bar divided by mc again. Okay, so this has no factor 2. And then I have 1 over r cubed. Okay, so what is this? This is twice a Bohr magneton square divided by r cubed. Okay, so it's of the order of magnitude of the dipole-dipole interaction between two Bohr magnetons at a distance r. That's what, because you remember dipole-dipole go like 1 over r cubed. Now, if you put here the ball radius, to just have an order of magnitude of it, then you can estimate this object to be of the order of the Rydberg times alpha squared. So again, this reduction factor, fine structure constant square, so 10 to the minus 4 enters. So with respect to all the other terms in the Hamiltonian, this is of the order of Rydberg times alpha squared. This alpha square appears consistently in all relativistic corrections. So not only in the kinetic energy, but also in the spin-orbit coupling and in all other terms that you might derive from the Dirac equation. Now, why did I comment on this? Especially because you should be again worried about what happens in heavier atoms. Remember that the ball radius has a factor 1 over z in the denominator. Okay, so that's so in fact it is the in presence of a z, it becomes like this. Okay, essentially inner orbits, okay, in heavy atoms are typically with an effective ball radius that is reduced by a factor z. You immediately realize that this, okay, makes a strong enhancement to the spin orbit coupling, because you get the factor z cubed. And also, by the way, there is also a factor z in the numerator, because also the electric field, okay, has an extra z here. So all to all, the spin orbit coupling gets magnified by a factor z to the 4th. Okay, this is just to justify a little bit the idea. Careful, heavy atoms, the electric field has a factor z, the magnetic, the ball radius gets decreased by a factor z, and because of this 1 over r cubed, the total factor in front is z to the 4. Okay, so account for spin orbit in heavy atoms. Otherwise, things are quite far off. Okay, so this is just a warning. Okay, good. So let's close for a while this part, and suppose that I now ask you, okay, so I have an hydrogen atom in absence of any magnetic field. Write the Hamiltonian, and then I should write not this, but I should write something like this: p squared over 2 mu minus say e squared over z over x, sorry, plus lambda spin orbit of r L dot s plus h other relativistic effects, okay? Including, for instance, the kinetic energy corrections that I described before, okay? So strictly speaking, even if there is no magnetic field, the spin is there, you see? It multiplies the angular momentum, and you have to account for it. You might say, where is it there? No, it's not there. I have to account for this effect. How? Well, in perturbation theory, because this is a small quantity. You see, it is a pretty small thing. So you will learn how to actually do the perturbative calculation and see how the resulting degeneracy goes later on when you will do perturbation theory. For the time being, I want you to learn something which has to do with the structure, okay, of the way this thing appears. So let's learn this, because it's a general construction. I hope I will be able to finish, because I want to absolutely to finish today this. Okay. So let's concentrate precisely on this n equal to subspace. Okay? You see that there are 1, 2, plus 6, 8 states total, okay? In fact, let me just concentrate on this. The reason why I don't consider this 2 is because L is 0 here. So in some sense, the spin-orbit coupling does not apply to these 2 states because L is 0. I mean, you can verify more precisely, but the basic reason is that if L is 0, the term is essentially ineffective. But here, L is 1, okay? So I have to worry about what happens to those 6 states. So the states are classified by N equal 2, L equal 1, okay? Then there is an M. Remember, M can be plus 1, 0, and minus 1. And obviously there is the spin, okay? So the spin is 1/2, and there is somehow the SZ, okay, which is plus or minus 1/2, up or down. These are the states, okay? Now, let me just write them in a more compact way. So there is an orbital part of the state, which is N equal 2, L equal 1, and then M. And then there is a spin part. You see, these are factorized states. They don't know about each other at this level, okay? So they are just factorized in the following way.
If we don't include spin orbit.
Absolutely. These are still the basic states that you can write. Then I have to find the correct states that somehow are better suited to any calculation that includes that term, okay? So far I start from this as basis states. So as written there, they are just written in this way, okay? Now, allow me to further simplify the notation. Too many things. So this object here, I will denote by, forget about N equal 2, I will denote as 1M, okay? And this object here, forget about the 1/2, I will denote it as plus or minus 1/2, okay? So this is the orbital part, and this is the spin part, okay? Let me just make it a table, okay? So I remind you, these are product states, okay? Let's see. I have 1 plus 1, the M is plus 1, times plus 1/2, up. Then I have 1, 0. I have to exhaust 6 states, right? 1, 0 up, but also 1 plus 1 down. Let me write them in this order. You will understand why I put them together here in a second. Then I have 1, 0 down, and then I have here 1 minus 1 up. Okay? And then I finally have 1 minus 1 the down. Okay? 1, 2, 3, 4, 5, 6. Okay, good. Why did I write them like this? Well, I have L and I have S. By the way, L, obviously, if you have it in isolation, you should think of L in the orbital times unity in the spin. Remember? Okay? L acts only in the orbital part. So whenever I have L, think of this. S is similarly unity in the orbital times S in the spin. Okay? In this case, however, L acts in the orbit and S in the spin part. So they act together. For instance, there is LZ, SZ. Then there is LX, SX, LY, SY. Or you could introduce L minus, L plus, S minus, S plus. So they change the orbital and spin content, the angular momentum values. They couple everything. However, let's consider the following strange object. It is L plus S. Okay? Now you might say, look, L acts on the orbit, S acts on the spin. How do you sum apples and pears? No. I mean, you can always think of them as in this extended tensor prop. So this is L times 1 in the spin, and this is 1 in the orbit times S. Okay? So this is a reasonable operator, although I don't want to make the notation too heavy. Is it clear? Okay. Now, is this an angular momentum?
Yes.
It is an angular momentum because all you have to verify is that J alpha, J beta is equal to psi, H bar, epsilon, alpha, beta, gamma, J beta, J gamma, right? Okay, good. Is this true? Of course it is true, because L and S commute. L obeys this, S obeys this. It takes 1 second to verify that indeed the sum of L and S, although acting on different subspace, precisely verified it. So, out of 2 angular momenta, L and S, by summing them, you obtain a new angular momentum, which is called the total angular momentum, which is also an angular momentum. And therefore, it has to obey to our general theorem about its eigenvalues and eigenvectors. Remember, in fact, I already called them J during the lecture. Okay? So, this could be integer or half integer. And correspondingly, Jz should be from minus J to J in steps of 1. Okay? So, everything has already been spelled out. Now, you might ask, why do you introduce this object? Well, for the following reason. Yes. Remind you, L dot S, it's an ST object on one hand. Let me do it here. Because L dot S, it is actually equal to LZ SZ plus XX plus YY, and if you rewrite it in terms of ladder operator, you find L plus S minus plus L minus S plus. Okay? Verify that if you introduce plus and minus as combination of X and Y, and you do a little bit of algebra, there is the thing. Okay? So when LS acts on any of the states, okay, what it does? Well, this object does no harm because it's diagonal. Okay? But this object is very bad because, for instance, suppose that you start from this state 1, 0 plus. Okay? So 1, 0 plus 1/2. Let's see. This object here, okay, acts on the spin, lowering it. Okay? So it gives you the minus. On the other hand, this acts on the spin, acts on the momentum by putting it higher. And remember, there is a square root of 1, 1. Okay? So in fact, the action of this changes the state, and it couples to this state that I wrote to the right. Okay? And this happens for all these 4 objects there. So somehow, while they are nice product state until L and S don't talk to each other, as soon as you have a term like this, they are mixed in some sense. Okay, so we want to know what is the right mixture of states that we should really form to solve the problem easily. Okay, this is one aspect of the study. The second aspect is the following. If you calculate J square, okay, from this expression, you find L plus S square, which is L square plus S square plus 2L dot S. Now you might be worried, but these are operators. They are yes, but they live on different spaces. So the formula is precisely the same as for the square of a binomial. Okay? So I might ask you, how much is L square? Well, L square is obvious. All the states have L equal 1. So all of them are eigenstate of L square with eigenvalue L plus 1, which is precisely 2 for all those states. How much is L square? Well, S square. S square, all speed 1/2 states, so this is S times S plus 1, but S is 1/2, so this is 3/4. All of them are eigenstate of L square and S square. So L square and S square, they are nice. Okay? The point is that, however, these are eigenstates also of Lz and of Sz. Okay? The product states are eigenstates of Lz and Sz. But you see here that the object that I want is in fact strongly related to J. Okay? You can say that L dot S, which is this operator that appears in the Hamiltonian, is in fact equal to J square minus L square minus S square divided by 2. Okay? So you see quite clearly, without even doing too many calculations, that what you have to do is to form eigenstates of J squared. You might say, and how do I do it? We'll see in a second. Okay? So out of this product state, the goal is to form eigenstate of J squared. And what else? Well, and Jz. Okay? So let's try to construct combinations of those states that are eigenstate of J squared and Jz. If you do so, automatically L dot S is simple. The effect is simple in those states. Now, let's look at Jz first. Jz is quite straightforward because Jz is Lz plus Sz, right? So let's see. What is the Jz of this state? 1 plus 1/2, right? Is it clear? Yeah. So 3/2. What is the Jz of this state? 0 plus 1/2. And of this, 1 minus 1/2. So both have 1/2. That's why I wrote them in the line. What about this? 0 minus 1/2. Minus 1 plus 1/2, both minus 1/2. What about the last? Minus 3/2. Okay? Okay, now we are quite in good shape. So these are eigenstates of Jz already. But they are not eigenstate of J squared. Because, I mean, by definition, they are eigenstate of Lz, Sz, L squared, and S squared. So let's try to extract the right combinations which are eigenstate of J squared. How do we do it? Any suggestion?
Write J in terms of raising and lowering.
Well, yes. In particular, start from, look at this state, okay? This is a product state. And it has Jz equal to 3/2. So I might ask you, is this an eigenstate of J squared? This is the question. If this object is an eigenstate of J squared.
Yes.
Yeah, why?
Because it's the maximum value of J.
This is the maximum value of Jz you can have.
Yeah.
So obviously it must correspond to some
J
value of J, and what J could be? J should be 3/2. Okay? So automatically what you have, this is the Jz equal to 3/2, J equal to 3/2 state. Is it clear? Now, If it is not clear, let's verify. So this is a state that I write as 1 plus 1 spin out. Okay? So let's try to calculate J squared. J squared is L squared plus S squared plus, so let's calculate L squared of this object. How much it is? This has eigenvalue 2, okay? So it is equal to 2, the same thing. What about S squared? S squared is 3/4, okay? Good. So all I need to calculate is the remaining term, which is L dot S. Now, 2 L dot S. Okay, so let's write it like this. Okay? Now let's see what I write it here. 2 L dot S of the state 1 plus 1 plus 1/2. Let's try to verify it. Let's see. What about the first piece? The first piece is 2 LZ times SZ. LZ is 1, SZ is 1/2. So it's 1/2 times 2. So this is 1 plus 1 plus 1/2. Okay? This is the first term. Now what about the extra piece? L plus. Well, L plus gives you 0. Nothing. L minus might give you something, but here there is S plus. And S plus gives you 0. Okay? So this nasty off-diagonal term, in fact, doesn't act on the state. So the result is that 2L dot S is simply 1 times the same state. Okay? So let's sum 2L dot S on the state equal to 1 times the same state. 2 plus 3/4 plus 1. Okay? So it's 3 plus 3/4. Let's see how much it is. 4. This is 12, 15 over 4. Okay? So the result of the L squared plus S squared plus 2L dot S is 15 over 4. And if you do 3/2 times 3/2 plus 1, which is the official number that this J squared should have, you verify that this is 15 over 4. Okay? Now, either way, okay, you should be strongly convinced that this state is in fact not only an eigenstate of Jz with eigenvalue 1/2, but also an eigenstate which has total angular momentum J equal to 3/2. Clear? Okay. We have found this. Next, remember, there is a technique. You spot the top state and then you decrease. That's exactly what we need to do. Okay? So let's learn how to find, for instance, how to find the next orbit, the next level in the list. And you will see that it is a precise combination of these two states. Okay? You'll see in a second. So, I calculate J minus of this state, okay, which has, in some sense, I can write it as J equal to 3/2, Jz equal to 3/2 as well, or in terms of L and S. Now, I remind you that J minus of a state is the square root of J plus 1 minus Jz minus 1 times same object, and this reduced to 1/2. Okay? So in order to construct this, I just have to apply J minus and remind us about this factor, okay? Which I can calculate easily. If j is equal to 3/2, let's see, and jz is 3/2, this is the square root of 3/2 times 3/2 plus 1 minus 3/2 times 1/2, right? No, times 1. Okay, so this is 3/2 cancels that, and this is the square root of 3. So the square root of 3/2. Okay? Good.
No,
So, yeah,
without the square root.
without the square root. Without the square root?
Yeah. It's 9/4 left inside the square root.
Yes. Yes. Did I do things correctly? Something strange. Did I do the calculation correctly? 3/2 minus 1/2 is 1 minus 3/2. This is 3/2 times 3/2 plus 1. Yes. It looks correct, right? Well, I have a question mark. Okay, we'll see later on. I have a question mark because this should be just 1 over square root of 3. Help me to fish the mistake. This should be okay, 3/2 is 2/2 is 1. So this is minus 3/2. There's no mistake in
Is
here.
it because we didn't is it because we didn't normalize the first one?
The first is normalized
Everything is
automatically.
normalized.
Because this is normalized, and they live in different space. So this is already normalized. Okay?
No, it's 3/2.
Yeah.
Definitely.
Yeah. It should, however, be. Well, let's leave the square root issue aside. Let's calculate this object here. Okay? So this object is L minus plus S minus. Okay? And this is the state written like that. So if you do this calculation, you have L minus times 1 plus 1 plus 1/2 plus S minus times 1 plus 1/2 plus 1/2. Okay? So N minus gives you square root of 2 times 1, 0 plus 1/2. And S minus acts on this thing and gives you 1 plus 1 minus 1/2. Did you follow? Okay? So this is the effect of applying J minus, which is the sum of these two, to this product state. Okay. Now, now this had to be no, there's something wrong here. Look, I don't know what I did, but if you put here 3/2, I have square root of 3/2 squared plus 3/2, and here I have minus 3/2 squared plus
3/2.
no, of course there is something wrong. There is no 1/2 there, sorry.
Oh.
Okay, we discovered the problem. So this is not, this is now Jz is 3/2 minus 1, so it's 1/2, so this is 3/4. Okay? If you do the calculation, this object has to be, I'll do it in this way. So this is plus 3/2. So this and this goes, is square root of 3. I'm sorry. Okay? So you see that, just a minute error can make things very strange. Okay, good. I put here square root of 3. Okay? Okay, good. So, what is this object? It's 1 over square root of 3, this. Okay? So, I write it like this. And this object, I just calculated, is there. Okay? So, end result, should I write it here? I'm a bit confused today with the blackboard. So, Jz equal to 1/2 is equal to 1 over square root of 3, so square root of 2 over 3, the first state, plus 1/2, plus 1 over square root of 3, 1 plus 1, minus 1/2. Okay? Notice, this state here is obviously a state with Jz equal to 1/2, and is a precise combination of these two objects. So this with the square root of 2/3, in fact, and this with the square root of 1/3. Okay? So taking this combination, you do not only have a Jz equal to 3/2, but also J equal to 3/2. Okay? And you can go on and calculate, I don't know how we type pretty badly. You can calculate the other one, so you can calculate the J equal to 3/2, Jz equal to minus 1/2, okay? And you would notice, if you do the same trick, square roots and L minus and S minus, that it comes essentially square root of 1/3 this, and again square root of 2/3 this. Okay? So, and finally, if you apply J minus once more, you get this state with coefficient 1. So these combinations here are automatically good eigenstate of Jz. And you might say, but there must be two other states, obviously. And the two other states must have, let's see, what angular momentum J they should have. We used one combination of Jz equal to 1/2 and one of Jz equal to minus 1/2.
Minus sign.
But there is another combination, right?
Minus sign.
So there is another combination, independent of the factor and the minus, there is certainly one other combination still with Jz equal to 1/2, right? And therefore, I should be able to form also a state with J equal to 1/2 and Jz equal to plus 1/2. Let's try to guess what it is. Okay? There are at least two ways of determining what is the correct combination that has, notice, here I have J equal to 1/2, while here J is 3/2. Okay, so don't be mistaken. These are not the same states. They should have a different combination. Now the solution is, in fact, simple. There are a couple of possibilities. One is the following. Write alpha times 1, 0 plus 1/2 plus beta, the other one, which is 1, 1 minus 1/2, and try to impose that this state is orthogonal to this. After all, they belong to, they are eigenstates of an Hermitian operator with a different eigenvalue. Okay? So they should be orthogonal. And if you write the orthogonality requirement, you will understand that alpha must be equal to 1, this is equal to, for instance, minus 1 over root 3, and this is equal to square root of 2/3. Okay? So if you calculate this times that minus the first one times that, you get 0. Okay? So in some sense, there is an exchange of objects in here. So this becomes the minus square root of 2/3, and this becomes the square root of 1/3. Okay? So the exchange value and with an extra minus. And the same happens here. Again, they okay. Of course, you can apply j minus to that and get it immediately, but if I have to write it for you, I think that this becomes, yes, this becomes square root of 2/3, okay? And this becomes minus square root of 1/3. So it's a similar thing. They exchange the coefficient and they get a minus sign. Obviously, you could put the minus either here or there. That's just up to you. You can multiply everything by a minus sign in front. That would be the same solution, no? Okay? Now, what did we learn from this exercise? We learned that if we renounce to working with product state, and we start considering eigenstate of j square and jz, we do have a different structure of the states. In particular, notice that eigenstate of jz, which are not maximal, do involve superposition of orbital times spin in two different flavors. You see? These are called entangled state. So in some sense, these states are, they require a correlated effect of spin and orbit. You see? The orbit 0 goes with the spin up, and the orbit +1 with the spin down. Okay? So when we discussed the problem of, if you remember, product versus entangled state, in tracing out the spin, tracing out the orbital part to measure the value of the spin, if you go back to that discussion, you will see that ignoring the orbital degrees of freedom when you calculate the average spin leads to a density matrix for the orbit, which is not a pure state density matrix. Is inherently a mixed state. And in fact, you see that the matrix element of diagonal in that discussion has an overlap between this and that, which is in fact 0. Okay? So the off-diagonal terms of the density matrix will exactly vanish in that case. So it is actually a mixed state, a full mixed state. So by ignoring orbital degrees of freedom in calculating only the spin expectation value, you realize that you cannot deal with the spin pure state, but you have to somehow account for this correlation into a mixed state of state. Okay, I think we will continue next time to finish the story, because now we are kind of tired. But essentially, these are the correct combination to account for the effect of this object. Because, let me just give you in a snapshot the idea. The idea is that if I use j square and jz, what you have is that the coupling term is plus lambda j squared minus f squared minus s squared divided by 2, right? And now, on the eigenstate with j equal to 3/2, this has a certain value. And 4 states, because remember this is 3/2, have a certain value. And the other 2 have a smaller value. So here, this object is 3/2, sorry, 3/2 times 3/2 plus 1, which is 15/4. And here, on this j equal to 1/2, the value is 3/4. Okay? So in some sense, while these two objects are the same, the spin with a larger j are shifted upwards, and the spin with the smaller j will be shifted downwards in perturbation theory. So this 6 for the general state splits into a quadruplet and a doublet. You will understand this later on in perturbation theory. But the idea is that in some sense, by constructing the right combination, you will see that the perturbative calculation is 1,9. While if you don't do so, you do have a matrix to diagonalize. And what we effectively did is we diagonalized that perturbation matrix, okay? In a way that uses somehow the addition of angular momentum. Now, let me just finish with one word. The technique that we just saw is very general, okay? For instance, I can ask you, you have two particles with a spin 1/2, okay? Try to calculate the total spin, so S1 plus S2. Again, you have to add angular momenta in the way I showed to you, and the exercise that I asked you to do is to show that you can form, out of 2 times 2, so 4 states, you can form 3 states with total spin 1, and 1 state with total spin 0, okay? So the exercise that is indicated in the notes is to construct the triplet and the singlet state out of 2 spins. Very, very simple exercise, but it shows that the construction we just gave is in fact more general. You can sum 2 spins together. You can sum 2 orbital angular momenta together if you have 2 electrons in the shell of the ion, of the atom, okay? So you can sum in general any 2 pairs of angular momenta with a technique that is essentially identical. You start from the list of product state, you take the upmost object, okay? You realize that this is also an area state of the appropriate J, and then you apply J minus, okay? It's a bit boring, but straightforward in principle. You have to take care of all the square roots without getting them wrong. The resultant coefficient, by the way, they are called Clebsch-Gordon coefficient. They are tabulated, in fact, okay? So all this is to tell you that, in principle, you can actually materially construct them with a bit of labor. Obviously, if I then ask you, okay, please go and check what are the right coefficients, you just go to Google and the table of Clebsch-Gordon coefficient will magically appear to you. But you can reconstruct it for a given case by just doing things like the one that I have indicated. Okay? All right. So I'll see you on Thursday.